Well, hello, popcorns. Nice to have you back. For this session, I'll be looking at still on acids and alkalis, but talking mainly on pH scale and universal indicator solution. Welcome back. And if you've not yet liked or shared my channel, please do like and share. And this would be really, really helpful. Thank you. Right, so let's just carry on really quickly. Okay, so for the purpose of today's session, I'll be talking more about pH scale and universal indicator. Now, most of the words that I'll be using are words like pH scale. I'm just going to highlight that. So pH scale, I'll use that a lot, which is a scale that goes from 0 to 14. Now, even though I'm saying 0 to 14, there are some schools that might use 1 to 14, right? So I've seen cases where 0 to 14 has been used, 1 to 14 has been used, whichever one that is being used in your school. So if you're someone who is still going to school, please use the one that is being used in your school. Or if you're just an adult, just topping up what you already know or what you've been taught, I'm sure no one's going to punish you if you said 0 or you said 1. The most important thing is it stops at 14. Okay, then the next word I would use a lot is saying that a solution is acidic, and that is when it has a pH less than 7. The next word I will use a lot is alkaline. Okay, again, and last one is solution has a pH greater than 7. And I will use the word neutral a lot. This is when a solution has a pH of 7. Nothing more, nothing less, just 7. Next one is concentration. Concentration is just the amount of chemical dissolved in a certain volume of solution. Okay. For example, if I have I can have 7 grams of salt dissolved in 10 ml of water, or in another container, 12 grams of salt dissolved in 10 ml of water. The one that has more amount of salt being dissolved in the 10 ml of water is the more concentrated one. So the ml of water, which is the volume of water, is the same. 10 ml in both containers, but the one with more grams of salt is more concentrated. So that is you talking about concentration. Okay, but when we get to that stage, I will explain more. Right, so these are the words I'll be using, and let's move on to the full session. Guys, please like and share. Also, really important to subscribe if you're watching and you've never subscribed. Thank you so much for those that have already subscribed. Okay, so when we talk about pH, let me just change my color palette. pH written like that. And what does that word pH mean? pH just means potential of hydrogen. Okay, pH means potential of hydrogen. Now, we know that acids release hydrogens, okay, when they dissolve in a solution. All right, so acids contain hydrogen, and that is what they release when they are in a solution. So the pH scale then was created with acid in mind. Okay, so based on the number of or the amount of hydrogen that it contains was how a pH scale was created. Okay, so the pH scale, for the purpose of this session, I will use 0 to 14. pH scale is 0 to 14. And this is what it would look like. So let's slide that up a bit. So looks something like that. We have 14 there, starts from 0. So in case you are asked to draw a pH scale, it must always stop at 14. Even if you're going to start from 1, fine, but it must stop at 14. Then the middle, which tells us that a solution is neutral, must be 7. Okay, and then you can fill in the other numbers. So here we would have 1, 2, 3, 4, 5, and then 6. And here would have 8, 9, 10, 11, 12, and 13. Okay, so that is exactly what a pH scale looks like. Now, remember we said that the word pH means potential hydrogen. Okay, potential of hydrogen. Now I'll start from the here, okay, and heading in that direction, it has more hydrogen. From my 6 to 5 to 4 to 3 to 1. Okay, the further down go to the left, which means the smaller the number, the pH number, the more potential, the potential of more hydrogen. Okay, and if I come here, heading to the right, okay, higher the pH number, again, less hydrogen. Less hydrogen. Okay. Or you can say the higher the concentration of hydrogen, the lower the pH. The lower the concentration of hydrogen, the higher the pH. Okay. Now, the one that is less than 7, so the higher the concentration of hydrogen, and in fact, I think what I'll write is higher concentration of hydrogen. So let me get into using the word higher instead of more. I'll leave the more. Underneath, I'll write higher concentration. Alright guys, please make sure you subscribe if you haven't subscribed yet. This will be really helpful to push my channel forward. Thank you, thank you, thank you. Okay, so from 6543210, we have more hydrogen. Okay, that means that it's a higher concentration. 8, 9, 10, 11, 12, as it goes up, lower concentration. And remember, this is lower concentration in terms of the hydrogen potential. Okay, so lower concentration of hydrogen. Now, if it is lower concentration of hydrogen, okay, we will then say that the ones on the left, the pH is acidic. Okay, so this is less than pH 7. And what does that mean? Acidic. But on this side, it is more than pH 7, more than pH 7, and that means that it is alkaline. Okay. Now, our 7 is exactly neutral. Okay, so it has to be exactly pH 7, I'll bring my arrow down here like so and would write pH 7. If you are given 6.9, that is not neutral. It might be close to neutral, but it is not neutral. Okay, so if you are given 6.7, again, that is not neutral. If you're given 7.1, that's not neutral either. It has to be just 7. So I'm going to write exactly pH 7 is neutral. All right. So with that being said, the pH scale will go from 1 to 14. Some will say 0 to 14. That will be fine. 7 is neutral. Okay. The higher the concentration of hydrogen, then we can say that the lower the pH. All right. So for example, pH 1 has a higher concentration of hydrogen than pH 6. Okay. Now the next thing we're going to look at is the pH going up in factors of 10. Okay. So I will put up a pH scale. In fact, I'll just draw one in here. Okay, let's push this up. Okay, drawing my pH scale again. So the center, the middle is 7, is 0, I'll use 14. Then we have 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14. Okay, so that one is too far away. Right. So pH scale goes up in a factor of 13, in a factor of 10, and I'll show you what that means in a second. So, for example, an acid of pH 2 is 10 times greater than or 10 times more acidic than an acid of pH 3. Or if I'm going for an acid of pH 4, okay, so an acid of pH 3, that there will be times 10. Right? So what that means now, I'll write that in words. Okay. So an acid of pH 3 is 10 times greater or 10 times more acidic. I would rather use the word more acidic. So 10 times more acidic than an acid of pH 4. Okay, now you could be given an acid of pH 7, sorry, an acid of pH 6, and asked to compare it with an acid of pH 4, and that will be 100 times, okay, because every step is 10 times. Okay? 10 times more, 10 times more. And we can also talk in terms of being alkaline, right? So if I go from, let's say, a solution of pH 10, so let's say pH 12. Now, to go from 10 to 11, that is 10 times, so times 10. Then from 11 to 12, that's another times 10. And altogether, that is 100 times, okay? So I will then say that an alkali an alkali of pH 12 is more alkaline than pH 10 by 100 times. Okay, because we had two steps to go from 10 to 12. Right? So for every step, it is times 10. Every step times 10. So if you have two steps between 10 and 12, then that is 10 times 10, that is 100. Okay, and that is 100 times more alkaline, or if you're talking in terms of being acidic, 10 times more or 10 times less, okay, depending on the direction you're going. So for example, 5, a pH 5, all right, is 100 times less acidic than a pH 3. And it's 100 times because for you to go from 5 to 3, you will have to go 5 to 4 first, which is times 10, and then 4 to 3 times another 10, okay, making 100. So pH 5 is 100 times less acidic than a pH 3. Okay, so the pH scale goes up in factors of 10. That is just to summarize what I have said in that part. And then the more alkaline a solution is, the higher the pH value. The more acidic a solution is, the lower the pH value. Okay. So let's just take a look at some pH, like some solutions, for example. So examples of solutions that you can be given and how would refer to those solutions. So an example is if you are given a solution, if you are told that a solution has pH 5, right? Or let's even say pH 4, then we'll say it's acidic. Okay? If we're told that we have a cleaning solution, a cleaning product, so a solution of pH 8, that is alkaline. Okay? Water, a solution of pH exactly 7, that is neutral. Okay? And one example is often water. And then a solution pH, let's say 6.5. Okay, now bearing in mind that this is not 6, okay, but 6.5, it is still acidic, right? Now, if you were given a solution of pH 7.5, that is alkaline. Once it has gone past 7, even if it's by 0.1, that is alkaline. Okay. Another misconception I would love to just quickly mention. If in an exam you were told that you have water, okay? Now most students obviously believe that water is neutral. Yes, it should be neutral, but it said to you that the water has a pH of 6.9, right? That is not neutral. As long as it is not 7, it is not neutral. So it is acidic. Even though it is slightly acidic, it is acidic because that is 6.9. Okay, so we have spoken about the pH scale. We've spoken about the factors. The next thing we're going to talk about will be the universal indicator. Okay, so when it comes to the universal indicator, we have already spoken about indicators in the last time, but what are universal indicators? Let's move my board up a little bit. I'm just going to go back and check to make sure. Screen it. Alright, that's fine. Okay, so universal indicator. Most acids and alkalis, right, are often colorless. Like literally, if you're looking at them in the container, you can't tell whether it's an acid or an alkali until you move close and carry out a test. Okay, so how do we test for to know whether it's acid or alkali? We'll use something called indicator. Okay, so with the indicator will give us a color change, and that tells us whether it's an acid or an alkali. Now, a universal indicator is often used. Okay, universal indicator can be in a paper form or solution form. So, universal indicator, okay, it can be a solution or it can be a paper. Obviously, not just any kind of paper, papers that are specially designed for this. Okay, so what these universal indicators contain is that they have a dye, okay, that would change in color depending on the type of pH solution they are in. Okay, so that means then because it is universal, you have a range of colors. Okay, so the common colors that we tend to find on the universal indicator from ranging from your 0 to 14. Your universal indicator, so let's go like so and like so. So 0, got 7, and then we've got 14 again. Now, you would find red, orange, okay, yellow, then green, blue, and then purple. So in that order, but obviously the shade ranges as you go up. Okay, so the color change on your universal indicator, for example, the paper, you compare it to like you would have like another paper on the side, okay, that contains varying colors that you can put side by side to test and compare. So let's say, for example, I'm given a universal indicator indicator paper, which sometimes would look like a yellow color. I'll put that yellow inverse indicator in a solution, and then once I bring it out, there should be a color change. I'll place that next to a chart which has all of the colors that you can possibly get, okay, and then you compare. And then the one that it is closest to, that will be what solution that is. So let me do a quick sketch here. So let's say that's my litmus paper. That's a really wonky one. Should look more like this. All right, that looks better. And then, and let's say that's my solution. All right. Now on the side, I will have like a chart that shows me a color range. So all of these little pies will be of different colors, right? So if it is red, I should have a pH 1, pH 2, 3 should be about orange, 4 would also be orange, 5 will be about yellow, okay? Then we've got 6, 7, 8, 9, and so on. So that goes all the way around. So that will be my pH chart, okay? So that's what I would use to compare. Now here is my litmus paper or indicator paper, which is most likely yellow in color. Once I put it into this solution, okay, and I bring it out, if the color changes, let's say from yellow to red, okay, color changes from yellow to red, then that means that I'll take that paper, place it next to the chart, and see which color is it closest to. So I'll place my paper right next to the chart and compare. If it's very close to like a bright red, then I know that I've got a pH 1. If it's like dark red, pH 1, light red, pH 2, or if I happen to have an orange, that could be pH 3 or pH 4. Okay, so placing it right next to a chart for comparison. And then now that's literally the end of the session. I'm just going to do a quick recap of everything that we have covered. Okay. So we have spoken about most acids and alkalis being colorless, so therefore would use an indicator. So in fact, let me type in what we have discussed so far. I'll type it right here. So this is a summary of what we've covered. So I have said most acids and alkalis are colorless. Okay, so if they are colorless, what does that mean? They are identified by using indicators. Okay. And I also mentioned that pH is potential of hydrogen. That's what that stands for, right? And that is coming from the fact that acid contain hydrogen. So the more hydrogen they have, the more acidic the solution is. Okay, so the higher the concentration of hydrogen, the lower the pH value, right? The more acidic the solution. And for the purpose of this video, I've said the pH scale goes up and down by factors of 10. Okay. Right, so that brings us to the end of this video basically. Thank you guys for watching, and please like and subscribe. That would really help the video. Bye.